Peter, for the very kind introduction. Thank you very much to you, Juliana and Ralph, for inviting me this morning. I was super excited to be here and to give this talk this morning. Welcome everyone, welcome to this new edition of SLE, and thank you very much for joining this morning for this talk. When I have been invited, I decided to not really present you a very technical specific contribution, but rather to share with you the vision that we have my team, but also in collaboration with several colleagues over the world, and more specifically with one very close colleague that I'm working almost on a daily basis, who is Thijs van der Storm from CW, with who we are co-leading an associate team in between his group at CWI and my group at. And I'm super happy to see in this room many people that has been involved during their PhD, postdoc in the team. And I will, by the way, present some work that has been done by these different people. So if you have any question, maybe I can directly convey this question to the right people. And my objective by the end of this talk is really that there is only one time in software engineering, and so in software language engineering. So what I mean by this, when I'm referring to this notion of time, I'm referring to all the different kind of times that we can see in the different papers from the scientific literature. Each time we are providing new tools or new way of building tools, we try to characterize the base place where this tools is supposed to be used. And if you go through the literature, you can see many references to design time or development time, or even now training time, where we need to train our models before being included into the software systems, compile time, runtime, operation time, and so on and so on. And I had at some point some time to reflect on what do we mean by this time in software engineering. Is that really a step in the life cycle? That would mean that when we are in one time, we cannot be on the other times? Or is it more an activity, possibly an activity which is performed in parallel to other activities, meaning that we can be at the same moment in different times? Or is it just a tool? And for this, I try to make an exercise trying to build a very naive big picture of this different time in the context of software development. So in the context of software development, we are using a lot of different software systems. We are surrounded of software, both in our professional and personal life. So in a daily basis, we are relying on this as a end user. And as a end user, we are using these different systems in the so-called operation time. So operation time is when the software system is provided to the end user and can be directly used by the end user. And of course, this operation time is following a time where we build the software systems, right? Which is more referred as the development time. And during the last decade, we did a lot of work trying to make as smooth and automatic as possible the transition, the continuum in between the development and the operation times, trying to automate as much as possible with principal tools and methods provided in the context of DevOps for going from development to operation and back from operation to development, at the point that nowadays we have a very high release frequency of our different software systems. And now if I'm focusing on the development time, of course for developing a software system we usually need a lot of different stakeholders, and for trying to coordinate the different stakeholders and the different activities that they are performing during the development lifecycle, we put in place some methods. So here, for example, it's an illustration with the Scrum method, which is an agile method, but you can think to any kind of development methods that we are putting in place for mostly organizing ourselves as human in terms of activities that we need to perform for reaching a high quality software system at the end that can be deployed and delivered to the end user. But of course, all these different stakeholders are providing a lot of different artifacts. And we also need to coordinate not only the stakeholders, but the artifacts that they are building. And for doing this, we are using different tools and methods. The usual tools that we are using is a version control system, such as, for example, Git. But for using Git, we also need some methods for coordinating the way of using the tool. And for example, here I put an illustration of the Git flow, which is one way of managing the different branches and so on in Git in a given software project. Okay, so if we now focus on the different activities of these different methods and the different artifacts that are built, we can also see another dimension, which is more referred by design versus runtime. So what does that mean? So it can become more clearer if we take the example, for example, of the V lifecycle, where explicitly in the V lifecycle, main objective was to have a left branch where we build the system, where we design the system, and eventually where we implement the system, and a right branch where we try to evaluate what we design on the left one by doing some static analysis, but most often some dynamic analysis, doing some debugging, profiling, testing activities. And for all of this, we need to run the system. So we need to evaluate by running, executing the system, which is already runtime. So it's a runtime, which is during the development time, because we are still developing the system. But it's also a runtime that we use at operation time. I mean, if we know how to execute the system, it's a way of executing it while we are developing it, but it's also the way of executing it when we use it in some way. So runtime is already something that we can put in place both at development time and operation time. And this is also something that we can see in languages. When we build our languages, especially in the community of SLE, we build our languages having a syntactical domain, which is mostly used at design time for building our different programs or models with our domain-specific languages. But we also need to provide usually a runtime infrastructure, which can be in the form of a compiler that we use for evaluating, executing, running what we define in the context of the syntactical domain. And this runtime infrastructure can be used, again, at development time for doing some execution, for testing, for debugging, profiling, and so on, but also, of course, at operation time when we want to use the system. And last but not least, just to finish this very naive big picture, I also wanted to introduce another dimension, which is application versus domain engineering. Because, of course, when we engineer our software system, we engineer our a given application, but because we are developing and engineering very complex application, we need to rely some knowledge that we capitalized. And usually we are capitalizing this knowledge in a continuous way. And for this, we introduce another dimension, which is the domain engineering. The domain engineering is really when we capitalize this knowledge in very different forms. It can be, for example, through component, with component-based software engineering. So we capitalize our components that we reuse afterward for building a specific application. And we can reuse it for different applications. And as soon as we have many components, we need to deal in the complexity of these different components and to clearly specify when a configuration is relevant or not. And this, the software product line community working on this with many tools and methods for doing variability management. And this is also what we are doing in SLE. When we employ some domain-specific languages, we are in some way breakdown our software development lifecycle in two parts. The one where we use the domain-specific language, which is at the application engineering level, but there is also, beforehand, the time where we developed our domain-specific language, where we capitalize the knowledge that we have in a given domain, and which is more at the domain engineering level, and which is usually, again, a very continuous process where we continuously capitalize our knowledge in that domain. So it's pretty naive and probably incomplete, but it was just an attempt to try to put together all these different dimensions. And then continuing thinking about this, what became clear to me is that we are organizing ourselves according to this different dimension. So for example, if I'm Oh, and I've forgotten that now we are employing some AI models that we need to define and train beforehand we can use them, which is another way of seeing this difference in between domain and application engineering. So if we look at our community, basically we are more or less stick to this organization of the different dimension. And here are the different sub-communities of the software engineering community, where for all of these different sub-communities, we provided some principles, tools, methods that are really specific of the specific time that usually they try to target. And which is good. I mean, developing software is something very complex, and because it's very complex, we need, if we want to conquer, we need to divide. And it was very good to break down our own community in these different dimensions, different times, such as we can address the complexity of the development of software. And maybe the claim that I will try to explain afterward is that now we matured these different sub-communities, it's probably a good time to unite all of them, such as we can have a more exhaustive way of engineering our systems. And if we look at the consequence of this, that if we see the traditional we are basically inheriting from this organization. We are inheriting of this organization. It's basically the Conway law applied to ourselves. We divided our software engineering community in a certain organization that we are inheriting for the organization of the development of our complex software systems. And it's not new. I retrieved this paper from Luciano Baresi and Carlo Ghezzi in 2010. And in 2010, there was already recognizing that the wealth of methods and tools that are used at development time to forge software have no more use when the software enters the runtime stage. And what I was explaining in this paper is that, so we basically try to develop a given system in a given domain. So domain in the large sense. It can be the application domain, but it can be also the environment in which the system will be used. And we try to develop this system in a given domain, such as we satisfy the given requirements. And what they was acknowledging in this paper is that we, at development time, we try to provide the best quality software system that meet the requirements with regard to a given D, but the D, the domain, including the environment in which the system will be used, is continuously evolving and changing, which means that we continuously need to engineer our system for continue to meet and satisfy the requirements. And at that time, there was emphasizing mostly on the facts of the mobility. So D was changing because of the mobility, but nowadays is going way beyond only the mobility. But it's, and I will come back to this a little bit later, it's changing because we have very complex socio interaction with our systems, because we are involving in environment where there is some wicked phenomena that we need to consider and which are very difficult to analytically take into account beforehand when we develop our systems. And in the meantime, what we can observe is that we are taming a kind of what I call software hyper-agility. So hyper-agility is not the agility of the methods, like agile method, but it's the agility of the software itself. So software is moldable. It's one of the terms that people are using in the Smalltalk community. It's super moldable, and because that's moldable, we use this ability of being hyper-agile. It a kind of multi-dimensional space in which we are involving when we are developing because function points, and the number of function points is evolving over the time. There are constants to take into account, and probably new constants to include during the life cycle. Think, for example, to energy consumption. That was not a concern 10 years ago in most of the software project, and which is super important nowadays to include. So we need to take into account these new concerns over the time, which is most of the time very big. I mean, we are building very customizable or variable systems, such as we can meet different usage of the same system. We have a release frequency. I already mentioned this, but the release frequency of our software systems is really increasing and increasing again, at the point that we are basically continuously delivering our software systems as soon as there is a new contribution in the development time. We are targeting more and more execution platform, and we used to have software systems that was working or not, and which is not anymore the case. I mean, all our software systems are evolving in a correctness envelope, and we need to be very clear on this correctness envelope. And in that, systems adapt, but not anymore to a very fixed space of variable requirements that we used to define beforehand in the D that I was mentioning just in the slide before, during the development time, and then no changing for the rest of the life. But now the D is really changing, and it's changing most of the time due to an emerging change of changing requirements. And these requirements are changing because most of the time we are taking into account or driven by the incoming input data. So we have a domain in which our software systems, which is continuously evolving, and we need to take into account of this evolution. Which means that software engineering must embrace this new temporal adaptability, and this new temporal adaptability that we need to consider in the context of this multidimensional space, where we have all these different dimensions that are continuously evolving over the time. So that's lead to what I call the software engineering of my initial claim. And what I will try to present you is that we have a key cornerstone role in the SLE community, because this continuous software engineering can be driven at the language level, or can be capitalized at the language level, as we are always doing in the SLE community, such as we can continuous language-oriented software engineering. But let's start by continuous software engineering. So what I really mean by continuous software engineering is the fact that we are continuously engineering our software systems at the point that the time where we are engineering a software system which is not yet in production is nowadays just a corner case. I mean, the mainstream case is that we are engineering a system which is already in production. And of course, it's raising a lot of challenges for us. It's raising a lot of challenges for us because we need to break really the different silos that we created in our communities that I presented before. We need to cross-fertilize the contribution that has been done in all the different sub-communities of software engineering. And we need to be able to continuously reevaluate all the decisions that we are taking when we are developing our software systems. So it's raising a lot of challenges, but it's also providing a lot of opportunities for us. Because if we are engineering systems that are already in production, we can leverage on all the data that we can collect from the system in production. What I mean by this is that we can leverage all the telemetry data, or the usage data, or the runtime data that we can collect, such as we can be well aware of the environment in which the system is used, such as we can take into account activities when we are engineering our software systems. So it's raising a lot of challenges, but it's also giving us a lot of opportunities for trying to automate and better clarify the environment in which the system is eventually used. And in the context of the software engineering, I did some literature review, and there is a lot of work that has been done on the past years. So it's very recent. If we look, there is a lot of papers that try to leverage the runtime data for automating some debugging session, or for automating the generation of test cases. I mean, if you think about test cases, it's beforehand the definition of input data. Why we should invent this input data if we can collect them from the runtime data, which are definitely clarifying in which context the system is used. I mean, it's better to test our system according to the way that it is going to be used in production. Right? So it's for monitoring, it's the case for profiling, it's the case for debugging, the case for testing. There is a lot of work that is currently done in trying to cross-fertilize these different dimensions. So what does that mean for software language engineering? I mean, SLE is about providing language and it's definitely the place here where we try to define the future of the experience of our developers. Whoever are these developers, that can be software engineers, that can be domain experts, that can be scientists, that can even be citizen developers. For all of them, we need to shape the experience in the future that they will need for engineering in a continuous way the systems that they are building. And for this, I will, this was the main vision that I wanted to share with you. And now I will try to illustrate this vision with some work that we did in the past years and even months in that context, and just to present you how this vision is driving the different contributions that we are working in my team and in the context of the associate team with CWI. I will present you some work that has been done on self-adaptable languages, so to make sure that our software languages that we are building can continuously evolve, even dynamically and automatically. And then, as soon as we have this self-adaptable infrastructure, we can think about how we can coordinate the different languages, such as we can reason over the multidimensional space, and having some decision-making processes that take into account the global big picture, instead of just taking some optimal decision in our local concern, where we use one language for one specific concern of our software system. And eventually I will finish, if I have time, about the vision that we have in my group about the future of the ideas that we are providing on top of these software languages, that I will not call anymore only integrated development environment, but more integrated and continuous development environment. Okay, so let's start by the first part about self-adaptable languages. So this vision about self-adaptable languages is something that we presented at 3 years ago, and self-adaptable languages are basically languages that provide capabilities for abstracting the feedback loop, so the design and execution of the feedback loop, while performing some trade-off analysis. And if I jump a little bit into the details of this paper, we introduced two feedback loops. One which is a runtime feedback loop that leverage all the data that we can collect when we run our software system. So the program is going to be run, and in that context we can collect a lot of information in which context it's run. And from this we can basically dynamically adapt language, and more specifically the execution semantics of those language, such as we can cope with the evolution of the environment. And I will give you some details, some more details about this one. And another one, which is about the design feedback loop, is a feedback loop that leverages all the data that we can collect at design time in the IDE regarding the use of the language. And I'm not going to give you any details of this. I can just point to you that, for example, Juan de Lara in Madrid is working. There is some very recent papers that has been published on this feedback loop, and where the idea is basically to look at the usage of the language, such as we can detect, for example, some recurrent pattern that are really demonstrating that we are missing some abstraction in our language, and from this recurrent pattern of the use of the language, we can automatically verify some new abstraction in our domain-specific languages, which make the development of the domain-specific language continuous according to the usage of the language. But I'm not going to detail anymore. I really wanted to present some work that feedback loop, which has been basically the PhD of Gwendal Juno that defended 1 month ago. And during his PhD, he proposed two main contributions. One which is ASOS, which is a meta-language for specifying an adaptive operational semantics, which is then compiled in the form of an interpreter, which is embedded into a framework, which is called SIL, that operates the runtime feedback loop. So let me give you some details about this. So ASOS is something that has been done in collaboration with our colleague in Amsterdam, initially in CWI. Now they are moving in some universities in Amsterdam, but especially with Thomas and Damien, who are just here. So if you have any question about this, I will probably convey all the questions to basically a meta language which is based on modular structural operational semantics. So modular structural operational semantics has been introduced by Peter Morris in 2004, and we use this ability of modularly defining operational semantics for, in a modular way, defining the semantic rules, but also the different adaptation that we can apply at runtime for adapting the behavior or the interpretation on the way of interpreting the different constructs of a given language. Rules such as they can be applied before a given semantic rule, after a given semantic rule, or in replacement by specializing a specific semantic rule, and everything done according to a feedback loop where we leverage the environment in which the system is executed. And there is some formal definition of ASOS, such as we can support the analysis of some properties such as semantic determinism, termination, and completeness, with some limitation regarding this because there is some evolution at runtime. But everything, if you need some details, are directly on the paper that has been presented last year at SLE. Just to give you an example, this one example of the use of MSOS, with which you can define the semantic rules. And basically, semantic rules is attaching a rule to a pattern AST, and that we apply in terms of writing for involving the execution state of our system. And in addition to the semantic rule, we can define some adaptation rule that match a given condition. And when the condition is old, on a given pattern of the AST, of the abstract syntax tree, we can apply this adaptation rule either before, but also after, or in specializing the one that should be executed by default. So this is the meta model. So this is pretty simple in terms of meta model of ASOS. Basically, an adaptive operational semantics is composed of a set of semantic rules. This is only MSOS. And in addition to this, we added some adaptation modules that for applying an adaptation rule, which is a semantic rule expressed in a similar way than we do in MSOS, in addition to specify if it's before, after, or in replacement by specializing the semantic rules by default that should be applied. And then, when we have the adaptive compile this into an interpreter, which is taken into account by SILS, which is a language framework that basically apply the feedback loop. So in SIL, we have the MapK loop, so the monitoring, analysis, planning, and execution. And during the planning, we define an impact model that is used for analyzing what are the best adaptation rules to apply. When the set of adaptation rule has been selected according to a given context, then at the execution level, we can, when we match the different condition and the different pattern in our abstract syntax tree, we can apply the different rules that has been selected, either before, by replacement, or after the by default semantic rule. And in that context, we can change basically the way of interpreting our different language constructs according to environment and according to some trade-off that we capture into the impact model. So if you go into the paper, you will see that we apply it to several languages. I'm giving you here 3 of them. So I will start by Mini Java, which is a representative example of an imperative general purpose language, where we can basically reify everything that has been done in the context of approximate computing directly in the feedback loop of the language. So we can, for example, apply some loop perforation algorithm that usually we do it at the program level. So we need to implement this approximate computing technique directly into our program. And here we can capitalize it into the runtime infrastructure of our language, such as according to a trade-off in between the accuracy that we need. So for example, in the signal processing domain, we can play on the accuracy of the computations that we are performing according it will take, and we can automatically, according to a given environment, apply the right trade-off and the application of the different adaptation loop. So we did it also for a specialized version of HTML, which is an example of a more declarative language, where the idea was to implement some trade-off in between the quality of the web page, of the rendering, and the energy that we need for doing this rendering. And the energy is not directly coming from the pure rendering algorithm, but also from all the data that we are transferring in between the server and the client. And in that context, we can dynamically adapt, for example, the quality of the images, or even the images that we are downloading and rendering in our web page. Or we can also, so we can degrade the images, we can conditionally load more or less information into the web page. All of this for trying to save some transfer of data over the network and to save some energy, of course, with a trade-off with regard to the quality of the page eventually. And we also did it for a more DSL, domain-specific language, RobLang, which is a domain-specific language for specifying some mission for robots. It's an imperative domain-specific language where the trade-off was more about the time versus the energy. So the time for completing the mission with regard to the energy that we need to use on the battery of the robot. And sometimes there is some trade-off for saving some energy, even if the mission is taking more time. So for example, we can reduce the speed automatically of the motors according to the trade-offs that we have chosen. Okay, so now I presented this. I wanted to present you some other work that we did on the context of that vision, and especially in this context, we made adaptable the languages, but we made adaptable the semantics of the constructs, of the abstraction that we initially defined into our languages. But of course, there is some question on the way of engineering our abstraction directly into the languages that we are building. And we started to discuss with some colleagues 1 year ago, with regular discussion during 1 year about this question about how to engineer our abstraction nowadays. And we recognized that there was a lot of literature, for example, on the usefulness of the abstraction. I think we are all convinced in this room on the usefulness of the abstraction. At least if you're attending SLE, I hope that you're convinced on the usefulness of abstraction. But we acknowledge the fact that there was very few literature about processing for engineering those abstractions. And we decided to reflect a little bit on this, and especially nowadays in the context where we are continuously engineering our software system. So we did this work with some very close colleague on the past year, and we wrote a kind of white paper that has been published on arXiv. So if you want to look at this paper, it's abstraction engineering that you can retrieve on one of the key findings or the key message in this paper is that we jump into the details of the anatomy of the abstraction. And one of the things that we need to recognize nowadays is that the abstractions that we are using are not only defined by humans beforehand, as we used to do in the past, but they can be also inferred by the machine. When you're including some machine learning models into your software systems, at some point they are inferring some new abstractions that you need to combine with the ones that are made initially by the human. And those abstractions that are inferred, that can be inferred statically, but most of the time they are inferred dynamically. and they are not only inferred dynamically but continuously over the life cycle of the software. They are dynamically updated, or they are even dynamically created. And which is, of course, raising a lot of challenges for us, because now we not only have to deal with the abstractions that we are defining ourselves, but we need also to combine them with abstractions that are more inferred from machine learning models and AI component in general. Which means that we need to manage these abstractions that are dynamically discovered over the life cycle. And those abstractions are usually coming with a lot of uncertainty that we need also to take into account. And eventually, when we are able to manage this complexity and uncertainty coming from the abstractions that we are using, we need to compose them. And nowadays, we need to compose this different kind of abstraction. And it's very new for us. I mean, what does that mean? It's not super clear, basically, but this is actually what happened in the modern software systems that we are building. And another question beyond the composition of this different kind of abstraction is how we can reuse them, how we can reuse them in different contexts, which means how we can transfer the knowledge that we use for inferring those abstractions initially in new contexts for developing other kind of software systems. And this led to a big challenge that I wanted to share with you, which is something that we just started very few months ago, working on this, about the hybridization of the different kind of models that we are putting in place in our modern software system development, where we have models that use man-made abstraction and models where we use inferred abstraction. And this is pushing us to think about what is the unifying theory of both deductive reasoning, the way that we used to reason on our system. I first define my abstraction, and then I'm using this abstraction for reasoning on top of my system, with more inductive reasoning coming from data science, where the abstraction are inferred from the incoming data over the time. So I think it's one of the big challenges that we have in our community in the near future, where we can use in our languages this different kind of abstraction for doing some hybrid modeling. So hybrid modeling is really when we coordinate the use of these different kind of models. So how we can coordinate the use of models as we used to define in the model-driven engineering community, for example, and the models coming more from the machine learning and AI community. And we can even go beyond the hybrid modeling, but we can go to adaptive modeling, where we use one model for adapting the other kind of models. So how we can use, for example, machine learning models for trying to infer or to refine an analytical model, or vice versa, how we can use, for example, an analytical model for inferring or for tuning the hyperparameters of our machine learning models. So all such kind of scenarios are more and more prevalent in the software systems that we are developing. And right now, we don't have anything for dealing with this. I mean, we know pretty well how to do inductive reasoning, or how to do deductive reasoning, but really the cross-fertilization in between the two is a big challenge. And it's a bit challenge because it's also introduced some variability spaces, in the sense that I mentioned the uncertainty, but beyond the uncertainty, it's also coming from all the variabilities that we can find in our environment in which the different software systems are involving, and we need to take into account this variability. And beyond the variability management that we used to do, we introduced this term of deep. We should recognize that we have variability occurring in all the concerns, but more importantly, there is interaction in between these different variability spaces, and those interdependencies in between the variability spaces have impact on our software and system properties. And most of the time, we are locally reasoning on a given variability space, such as we can locally try to optimize our decision. What is the best decision that I have to do in this variability space? But we all know that accumulated set of local optimization is not going to provide a global optimization of all the concerns that we are putting in place in the development of our software systems. So we really need to capture these different variability spaces, interaction in between them, and being able to reason over these different dimensions and different variability spaces. So this is a vision that we presented a few months ago in a new conference, by the way, which is called REP, about reproducibility, which has been introduced by SIGSOFT, ACM SIGSOFT, and where there is many work that try to reduce this deep variability by trying to reduce the variability spaces and fixing a lot of things. Okay, so that's probably one way to do it, but to be honest, I'm not super confident that, it's something which is imposed to us. This variability is imposed to us, so we can try to remove it, but at some point it's going to fail. It's probably better to embrace it and to make sure that we can deal with this deep variability, which means that how we can formally or explicitly capture the different variability spaces, relationship in between them, and then providing some way of reasoning into this different variability spaces and interaction, such as we can find some global optimization over them. And in terms of global optimization, we can think about fixing one point in this multidimensional space, such as if we capture this configuration among the multidimensional space, we can reproduce the way of developing our software system, but more importantly, we can replicate in the sense that we can try to change a little bit and to play this variability space as we explore other alternatives, or we can try to optimize. So we can optimize the quality of our software system. We can also validate our software system, basically, for example, trying to have a better robustness of our software system, because we know that the environment is going to change, so we can play with this variability to know in which context is going to work and in which context is going to fail. And we can even provide more better resilience, because we know that we can change dynamically the configuration over the time, and it will still continuing to provide the quality that we are expecting according to the requirements. And of course, this leads to a better support of a feedback-driven software development, because if we are continuously engineering our software system, we need to take into account the feedback from all the data that we are collecting during operation time, such as we can continuously re-evaluate the different decisions that were taken during the development of our system and possibly change those decisions according to the change of the environment in which the system is behaving. And it is software development, but we also did it, so there is a paper where we introduce basically the fact that we need to capture the different variability spaces, but beyond capturing the different variability spaces, we should expose some impact model, such as we can have a global feedback loop that reason on top of this impact model for trying to find a global optimization. And this is true for software development, but it is also true for complex systems and more cyber-physical systems. So this is a paper that we presented at IRISA this year, which was a collaboration with Airbus, an aircraft, a European aircraft manufacturer, where we presented this and we tried to discuss with them the relevance or not of this feedback-driven support, and how they can put it in place in the context of their company. And definitely the key finding is that they definitely need to continuously reevaluate that they are taking when they are engineering the aircraft. And this continuous decision-making process is something which is currently very hard for them to handle, and this is what we are currently working with them for, providing them some support for this. So everything that I presented up to now was really building blocks, and all these building blocks need to be introduced into a continuous development environment, which in some way require to de-siloing software engineering with software language engineering, meaning in another way, we don't want to think outside the box. We want to just remove the box. Think about design time. If design time is also deploy time, it's also runtime. I mean, something which is super well known in the Smalltalk community, for example. If the ID is the environment, but also the language and the application itself, everything is mixed together. I mean, it's more or less modeling, it's more or less testing, it's more or less debugging or monitoring or whatever. And all of this need to be used by stakeholders like domain experts or software engineer, programmer, modeler, end user, developer. So everything should be supported by the future development environment that we are producing in support of the domain-specific languages that we are developing. So for this, the first thing that we did is in the context of a collaboration with several companies, especially Safran, which is an aircraft engine manufacturer in France, but also with a startup that we started, which is called Twin IT, and where we worked on an engineering forge, which is, let's see it as the next generation of the software forges that we are using nowadays in all the software projects, where we try to capture this design space across the different variability spaces and the interaction and interdependencies in between these different variability spaces, such as they can continuously, over the life cycle, re-evaluate the decisions that they have taken by trying to explore in this design space and to try to optimize the decisions that they are taking with regard to all the different concerns that are involved in the development process. And this is done in the context, it's 10-second publicity on my side, but this is done in the context of the startup Twin IT, where they really work on tools and methods for supporting this continuous software engineering or even cyber physical system engineering by producing the tools, but also the methods for using these different tools. So if you're interested about it in a more industrial context, you can contact me and I would be super happy to discuss with you. But the forge is only for coordinating the different artifacts and the different stakeholders, such as we can reason globally on our system. We also need to have the development environment itself. And for this, if we think today on what we expect from an environment that will continuously support the engineering of our software systems, is basically what we call the digital twin. A digital twin is supposed to be a digital representation of a physical twin. This physical twin can be a pure physical system, but most of the time it's not. It's most of the time a cyber physical system, where the part of the cyber and the physical part can be very variable. Sometimes there is a lot of physical part and a bit of cyber software, and sometimes it's a pure software system. So the physical twin in some way is absolutely not physical, but it's a pure software system. And here I'm just taking one figure from our colleague from Rennes, especially co-authored by Bernard, who is in the room, where they did a literature review and a mapping study of the different digital twins that are used and published in the literature. And what we can recognize from this, the digital twin are not only used during operation, but it's really a tool which is employed for seamlessly following the continuous engineering processes from design time to runtime. And of course, you can be more or less active or not on the physical twin according to the different phases, but it's really a tool that you use all along the engineering processes. And if we look at the art and soul of our digital twin, there is a lot of models. There is a lot of models that are playing very different roles. So, of course, there is some prescriptive models, which are the ones that we are building for prescribing the systems that we want to build. But because it's employed all along the engineering process, we can also leverage we can collect from the system or the environment of the system, such as we can also build some descriptive models and the context in which the software system or the system in general is used. And then we can use this descriptive model for supporting our work in the definition of the prescriptive model. So it can be done manually. So for example, using this through support like linters and so on for trying to support us in the decisions that we are making in the definition of the prescriptive model. But it can be also partially automated by the use of some predictive models, any kind of machine or symbolic statistical models or whatever that we use for supporting us and helping us in the definition of the prescriptive models. And I will finish with this. I'm asking you the question: what is the future of ID in that lens? In the sense that if we think about IDs as digital twin for software systems, I mean, how we can experience our software systems through the ID continuously all along the life cycle, right from the operation into the development. Like, for example, having linters that are fueled with runtime data, such as when we take some decision, when we program our software system, we can leverage all this runtime data. How we can cross-fertilize, for example, monitoring, debugging, and testing. I already mentioned this. I mean, there is no reason to define from scratch like this what are the relevant data for driving our debugging session or our test cases. I mean, there is no sense to just invent this runtime data as soon as we can just collect them from runtime because our system is already in operation. So I really want to raise this challenge for our community in the future and to think what should be the future of the IDs that we are providing on top of the domain-specific languages that we are defining. This was my last message. So just to conclude very quickly my my talk, I think, sorry, that I convinced you that time to tame and to our software systems and to cope with the software hyper-agility that I introduced, that we continuously need to explore and to reevaluate the different decisions that we did in the past with regard to a changing environment in which the system is evolving. And for this, I mean, because we need to address this new temporal adaptability that I introduced earlier. And for this, we need to go towards a continuous language-oriented, of course, software engineering. I just presented a few things that we did in with this vision. I mean, it was just some spot for demonstrating you the kind of work that we can do as soon as we have this vision in mind. But I really think that SLE is the right place for shaping the future of the experience of our developers, whoever are these developers. It can be software engineers, domain experts, citizens, developers. We are here for shaping the future of how they experience this continuous engineering of the software systems. And I mean, SLE is really the hometown where we cross-fertilize these different communities. I mean, it has been built by the cross-fertilization of programming language, of generative programming, of model-driven engineering, of PL, software product line, CBS, component-based software engineering, and ontology. And now I'm just asking, what about the adaptation loop? What about DevOps? I mean, how we can also leverage everything that they did in the context of the engineering of the languages that we are doing, such as we can have some more augmented language analysis tools like the recommenders, linters, and so on. We can also combine live and exploratory programming continuously, so we can explore many different alternatives in our ideas, and we can bring together monitoring, debugging, test, and all this kind of activities. Thank you very much for attending this talk, and of course I will be super happy to discuss you. I don't know if you have to answer some question, but more to receive from you some feedback about this vision, what you think about it, and yeah, I will be super happy to exchange with you. Thank you very much.
So we only have one microphone, so you can raise your hand if you have a question, and I will bring the microphone to you. You'll answer, and then I will bring it back to our presenter. Oh, more efficient. So I guess if you have a question, you can come up. or if you want me to bring it, I can bring it if that's preferred.
Thank you very much for your talk. So when I saw the languages that you had, where you could tweak the behavior of the program as things happen and so on, have you thought about how that would also change the testing frameworks that we use and the testing languages? Because it feels that instead of testing, giving these inputs, produce this output, you have to do more like property-based testing or like change your approach to testing altogether.
Thank you very much. We currently have a PhD student working in the context of scientific computing. And it was super interesting because the rationale at the beginning of this PhD was that, okay, we need to test our scientific models that we are using, by the way, for taking some decision on our daily life. I mean, we had a lockdown that has been decided by many governments based on scientific computing and the use of. And if you look, for example, at the last GIEC report, there is very few scientific models that are tested, and we try to understand why. And basically, in scientific computing, scientific models for running it is usually using high-performance computing for hours, days, or even weeks. And if we think about our test cases, I mean, if you think about GUnit, for example, or whatever, it's basically defining tens or hundreds or even thousands of test cases that are all running individually the software systems. How you can run thousands of time scientific models that take weeks or days, even days, for being run once. I mean, that doesn't make sense. And in that context, there is a lot of cross-fertilization in between the execution itself and how we can fuel some debugging activities and some test cases by minimizing the test cases that we try to infer from the actual execution. So the only experience that we have currently is in this context, but I'm pretty sure that we need to do it in other contexts. I gave some references in my talk, and all of them are ad hoc approaches that we also need to verify at the language level. How we can produce automatically the bridges in between these different tools from the specification of our languages and the coordination of those languages. So I really see a great future on this. I mean, it's super exciting in some way.
Thank you. Thanks for the talk. That was very interesting and inspiring at the end that SLE is the right place for a lot of this. But I was curious about the adaptive SOS, and you sort of think like, the motivation is I don't want to rewrite this whole specification with an adaptation. I want to have something that gets applied. And then, so my question is, does that sort of generate a new version of the plain SOS specification that then is used? But I don't think you do that. You sort of see the original one and the adaptation, and you read those sort of in combination to know what's happening. But do you do adaptations on top of adaptations? Do you get enough adaptations that you kind of lose an understanding of what the resulting SOS specification is? And do you want to sort of reify that adapted version so I can read that? Can you like talk about that a bit?
Yeah, thank you very much, Eric. So it's exactly this. If we look at the software systems that we are building, because we are evolving in a changing environment, most of the software systems need to embed a kind of feedback loop. In some software systems, I mean, it's a primary concern of the software system, the feedback loop. So think about an autonomous car. I mean, concern when you develop an autonomous car is to have a proper feedback loop and in to continue to implement it by hand at the time that you're developing the software systems. But there is many other software systems where the adaptation loop is not the primary concern. And it's not the primary concern at the point that the developer most of the time don't really know how to implement this feedback loop. It's not well done. And in all this context, we thought that it was a good idea to reify it at the level of the language infrastructure, such as the developer don't have anymore to deal with this concern. I mean, it's just implementing his regular system, and the virtual machine is basically implementing the feedback loop and changing the way of interpreting the different language constructs according to this environment. how it's done, we leverage modular SOS, such as we can modularly define our semantic rules, but also the adaptation rule. And everything is compiled case in a framework which is called SEALed. So SEAL is in Java. So all the semantic and adaptation rules are compiled to Java. And the SEAL framework is operating the feedback loop, doing the monitoring, analysis, and it's changing every time. And it's deciding the right adaptation. Then it applies different adaptation. If you put operational semantics as a set of writing rules from SOS classically, so there is a set of rules. Yeah. Okay. So there is a set of rules complemented with these adaptation rules. And now the question is, do we adapt the behavior at runtime? So which means applying these adaptation rules. So either in complement of the other ones, before or after, or just replacing the initial semantics. So that's the only thing that we are doing. And for this, we wanted to modularly define our structural operational semantics. And that's why we used modular SOS. And one of the benefits, for example, with modular SOS is that you don't have to deal with the complete execution state, but only the one which is relevant for the rules that you are currently defining. So that's the kind of thing that we leverage in ASOS from modular SOS. So basically, it's just a specific use of modular SOS. The only thing that we extended is this ability of defining adaptation rules that can be applied before, in a replacement, or after. That's the only thing that we did on top of MSOS. Everything else is just a regular use of MSOS, basically.
Can I just ask then, if you have before and after, this suggests distinct times. And your whole message was all times are the same. I'm just giving you a little grief. So.
Yeah, of course. Good comment. Is there any other question?
So if I may take the opportunity to have a question myself. First of all, thank you for the presentation. I was very happy to see this, but a lot of these things are far beyond my imagination even, let alone my work. And so some element of something I once did that's been of some use in this context. But if I think about practical experience with software packages and applications, one of the main irritations I've always found is the breaking changes that occur when new package versions arise, and the lack of immutable, reusable components in the software development world. Is this something you're embracing, that you have a breaking change and this has consequences and people have to patch things down the line? Or is it that you're aiming at some nirvana where you have these reusable components that stay the same and people can rely on them? There are two different strategies there, and I'm just wondering where you stand on this.
Yeah, so that's a very good question. I mean, I don't think that we can really decide which approach we want to choose, because there is one which is ambiguous in the sense that we need continuously to change our component, and of course that can imply some breaking changes on the software system itself. And that's exactly why it's super important to be able to experience our software system through the digital twin. The digital twin being the place where we can evaluate this breaking change, such as we can see what are the consequences to resolve these differences and eventually to deploy the change that we want on the software system. So this detachment in between the physical twin, which can be a software system, and the digital twin, where we can experience through this digital representation, is super important.
Yeah, thank you very much, Benoit. I also very much enjoyed your keynote. You made one point that this kind of classic view on software development also involves the idea that many of the early methods, like design methods, are suddenly then not important later on. And you also had this nice idea about the IDE being basically one place where it all comes together. I was just wondering, and then you had many nice methods at hand, like the adaptive models and semantics. I was just wondering, have you thought about using knowledge graph terminology and semantic reasoning, semantic data? Because much of what you say also seems to strike on what usually people emphasize in the AI context, like explainable AI, right? But some of what you explain could be seen as explainable software development. I mean, more than explanation, but explanation is also very important, right? And there's also this coming together of deductive and deductive reasoning also seems to call a little bit more for, a semantic data, semantic reasoning, symbolic AI approach. What do you think about this?
I think it was a very wise comment, and I think you said almost everything. I don't have to add anything. It's really a challenge for the future, but I think you're really right. And for example, we just started a few months ago a project where we try to deal with this model hybridization challenge, where knowledge graph is really at the heart of the project. So it's exactly the kind of solution that we are trying to experience for doing this. So I have no more to say because it's really future challenges, and I don't have any solution right now to present you. But it's exactly this. I mean, it's really a very wise comment and really well said and better said than what I did during the talk. Thank you very much, Ralph. But yeah.
So maybe that's a good point to conclude this session by thanking the keynote speaker for his wonderful presentation here. Please join me.